Hey folks, Mr. Miliano here. In this video, we'll be walking through the example problem that's shown here on this page. So I'm going to read it and then I'm going to walk you through my thought process. So the problem goes like this. I'm reading right here. Alice and Bob are both pulling on a 15.0 kilogram box with different horizontal ropes. Alice pulls with 55.0 newtons of tension force to the right, and Bob pulls with 20.0 newtons of tension force to the left. The box moves to the right and gets faster by 0.250 meters per second each second. Our goal is to determine the magnitude of the friction and normal forces that are exerted on the box by the floor. And as we solve this, we're going to be going through our force problem solving steps here. There's a whole bunch of them. But I'm going to walk you through what they are. We've already been practicing a lot of these, but they're all here in one place. So let's get started. Step one tells us to draw a well-labeled physical diagram of the situation. We've got a spot for that right here. You don't always have a spot, but this one does. So let's see, what is the situation? We have the floor. I'm gonna draw it like that. We have ourselves a box. And we have ourselves two people, Alice and Bob. Alice is pulling on this box to the right, so I'm going to draw a rope that looks like this. And then I'm going to draw Alice. She's going to look something like this. There we go. And there's a second rope, and Bob is pulling with 20 newtons of tension force to the left. And there's Bob sort of doing his thing. I'm going to label Alice with an A, Bob with a B. Cool, and that's our situation. One thing that's helpful in these physical diagrams is draw arrows for velocity and acceleration. This box is moving to the right. That means the velocity vector is pointing to the right. And it's getting faster, so we have an acceleration. And since it's getting fast, the acceleration is in the same direction as the velocity. And so our acceleration vector is also to the right. Cool, that's a nice looking physical diagram. Let's go ahead to step two. Identify the system that you'll analyze by drawing a dotted line around the object or collection of objects that make up your system. When I go and look here, I see the friction and normal forces that are on the box. The preposition on there is key. I want to know what's happening to the forces that are on the box. So my system will be the box. I am going to draw a dashed system boundary around my box. Great. Step three, where applicable, sketch the coordinate axes. Let's go ahead and do that. I usually like to make my coordinate axes match the direction of the acceleration, which is to the right. And so my x-axis is also going to be to the right, and then I'll make my y-axis up. Sometimes x to the left is helpful if your acceleration is to the left. Sometimes y is down is helpful if you're moving up and down. So different choices are helpful in different cases. Great. Let's move on. So sketch your coordinate axes and identify your sign conventions, indicating the designated positive directions on each axis. Done, did that. Number 5, write down your given information, including units and appropriate vector directions. All right, so write down everything that I'm given in a list here. I know the mass of this box is 15.0 kilograms. I'm gonna write all of my givens as some variable, I'll choose m, equals whatever number it has, 15.0 kilograms, whatever number it has and in whatever units, kilograms. So that's this one. Moving right along, I see I have a tension force of 55.0 newtons, and that's from Alice. So we have a tension force on, I'm using B for Bob. Can I call this C for crate? Tension force on the crate by Alice is a vector that has a magnitude of 55.0 newtons, and it is to the right. I should probably start a list of the subscripts I'm using. Let's go ahead and put those over here somewhere. I've got A is Alice, Got B is Bob. I've got C is crate. And that's all I've got right now. Great. Moving right along, looking for more numbers. I know this is a number, 20 newtons of tension force. That's on Bob, and it is to the left. Let's add it to our list. Tension force on the crate by Bob is a vector that has a magnitude or a strength that is 20 newtons, and the direction of that vector is to the left. Carrying on, the box moves to the right and gets faster by 0.25 meters per second each second. This kind of looks like a velocity, 0.25 meters per second, but the key is that this is telling us how much the velocity is going up each second. And so this is actually meters per second. This is an acceleration. So I'm going to write A vector equals 0.250 meters per second or meters per second squared. And I know that that vector is also to the right. That looks great. Sometimes I like to remind myself that G equals 9.81 newtons per kilogram is always a given, the strength of the Earth's gravitational field. Yeah, that ought to be good. And now, what am I trying to find? So let's see. Determine, that's the verb I'm looking for. Determine the magnitude. So I'm looking for how strong, for the friction and normal forces exerted on the box. So I'm going to go ahead actually and draw a divider line here and a divider line here. The things I'm trying to find. I want to find the friction force on the crate by the floor, ground, surface. I'm going to do S for surface, I think. And I want to know the normal force on the crate by that surface. And these are vectors that I don't know. So I'll say equals question mark. This is all getting my thoughts organized. How can I translate what's written and given to me in this paragraph into physics ideas? There we go. What's next on our to-do list? We've done that. We have written down the given information with units and vector directions. We wrote down what we were trying to find. That was step 6. Step 7, draw and label a force diagram in accordance with the guidelines that we've established in class. Let's do that. I am thinking about forces. I know that I have these two. The way I think about forces going from the physical diagram to the force diagram is I look at this boundary and I look at which things are crossing over that boundary, because a force is always an interaction between two objects, and the forces that go in my diagram are always an interaction with stuff inside the system, or between stuff that's in the system and stuff that's outside the system. And so I see this rope here is crossing the boundary, so that'll be a force. I see this rope here as crossing the boundary, so that'll be a force. I see this interaction between the floor and the box right at that boundary, so that'll be at least one force. So actually normal and friction, it'll be 2 forces. And so that's all my contact forces. And then the thing that's invisible that I didn't draw is that the box is also interacting with the gravitational field, so that'll be a force. And even if I really wanted to, I could somewhere in my picture draw some vector to the side that indicates that there's a gravitational field downward that's pulling on my box. Cool. Let's go ahead and draw some forces. I know that Alice is pulling to the right with a lot of tension. So there's the tension force on the crate by Alice. I know a few more things before I draw more. I know that Bob is pulling to the left. I know that because the box is moving to the right, that friction is to the left. So I'm going to have 2 forces to the left. And the other thing I know is that my acceleration is in the rightward direction. So I must have more total force to the right than I do to the left. I drew this tension force as 1, 2, 3, 4, 5, 6. So I want total to the left, everything I draw to be less than 6. So I'm going to go 3 and 2 as my choices. I'm going to draw, let's see, 1, 2, 3 as my tension force on the crate by Bob. And I'm going to draw 1 too long, my friction force on the crate by the surface. So 1, 2, 3 to the right, 1, 2 to the, or sorry, 1, 2, 3 to the left, 1, 2 to the left, that's 5 to the left, which is less than my 6 to the right. And I have that because my acceleration points to the right. And force diagrams, I like to, and I remember at least, to draw those as big, solid, filled-in arrows. Great. What else do I know? I know there's a gravitational force on the box pulling down. So on the crate by the Earth's gravitational field, I need to add that to my subscripts. Earth's gravitational field. I have an upward force on the box by the surface because the box is compressing the surface. So normal force, crate, surface. And I know that these two have the same strength because there is no change in motion vertically. The box is staying at the same horizontal position, so there's no vertical acceleration. So that's my force diagram. It looks something like that. Let's keep going. What's next? We drew a force diagram. That's number 7. Number 8, write an equation that describes the net force acting on your system based on the motion described in the problem. If the problem is two-dimensional, you should do this for both the x dimension and the y dimension. That's an if. If you only have to worry about one direction, you only have to do this for one thing. But we have two things. And then, so that's number 8, based on motion. Number 9, because we're going to do these together, says, in each dimension, determine the net force based on the force diagram. There's some examples there, but I'm going to go ahead and just do it. So I'm going to scroll up, shift the page up a little bit. Based on the motion, I am accelerating in the x direction. And so my motion equation is going to look something like, so based on Newton's second law, right, which is the acceleration is the net force over the mass. And that is, we can do that for each dimension, x, y, and z. I'm going to go ahead and write this by multiplying mass over and saying the net force in the x direction is mass times acceleration in the x direction. That'll be the helpful way to calculate. Often, that's how we'll write Newton's second law when calculating. This one's helpful for reasoning. This is helpful for calculating. So that's my based on motion in the x direction. In the y direction, I have no acceleration. And so it is true that net force in the y direction equals mass times acceleration, but that acceleration is 0. So I'm just going to say the net force is 0 in the y direction. Cool. From there, based on my force diagram, what do I have in my x direction? I have 3 arrows I'm adding together. I have this tension force arrow, tension force on the crate by Alice, and I'm adding that to this leftward arrow, the tension force on the crate by Bob. And I'm adding it to this arrow too, this leftward arrow, which is the friction force on the crate by the surface. And so that's my x direction forces. In the y direction, I just have 2 forces I'm worrying about. So adding up my force in the y direction, it looks like adding this upward arrow, the normal force on the crate by the surface, and the gravitational force on the crate by the Earth's gravitational field. Cool. So that's the vector equations. We're going to write scalar equations next. And for each vector that I have on the right side of the equals sign, I'm going to think, should I put a plus in front of it because that vector was pointing in the positive direction? Or should I put a minus in front of it because that vector was pointing in the minus direction? So let's go here. This tension force is in the right, so I'm going to put a plus in front of it. Tension force, crate, Alice. This tension force from Bob is to the left. It's in the minus direction. Tension force on the crate by Bob. This friction force also to the left, so it gets a minus in front of it. Let's do the y direction now, up and down. I chose up as my positive y direction, so this normal force gets a plus in front of it because it points up, and this gravitational force gets a minus in front of it because it points down. So that's the scalar equation. That's actually steps 10, 11, and 12 on this thing all put together. I'm perfectly happy if you skip right to 12, skipping past 10 and 11. If doing 10 and 11 help you, please go ahead. Sorry, we haven't done 12 yet, but we've done 10 and 11 together. Feel free to combine those. That's doing the scalar equation. That was force diagrams. Let's do it for the motion too. Acceleration is a vector, so MA will have a direction. It's to the right, so this is a positive MA. But you have to worry about the acceleration too. That should be a minus if the acceleration points opposite your positive direction. And then here, based on the motion, 0, positive, negative, 0, doesn't matter. Great. Next step is step 12 in this, which says put the results of the original equation together with the results from step 9. So 6 and 9 is basically motion was step 6. 9 was force diagram, put them together. So if MA is equal to net force from the motion, and these guys are equal to net force based on the diagram, put them together. I have positive MAX, subscript x, mass times acceleration in the x direction. That's equal to those three things. I have a tension force on the crate by Alice, minus a tension force on the crate by Bob, minus a friction force on the crate by the surface. Similarly here, I have 0 must be equal to the positive direction normal force on the crate by the surface minus the gravitational force on, this shouldn't be an S. We're looking at the crate here. This should be a C on the crate by the Earth's gravitational field. Excellent. Great. You'll do this every time. And most of this should happen without whatever the specific question is asking you for. Like you should be able to do a lot of this for every problem. And then you have a lot of tools set up to finally answer any question. And so if you read a question, you go, I don't know how to answer that. Great. Don't let that be a stopping point though. You know how to get started. You know to draw a picture, you know to draw a force diagram. Tell me what you're given, tell me what you want to find. Write out some force equations based on how things are moving and the diagram in each direction. And from there, usually a path forward starts to emerge. And so we are now ready to answer the specific question that was asked, which is, question 13 is to solve for the unknown force. It's not always a force, but solve for the unknown quantities. And then while I'm here, I'll mention step 14 says all the rules apply for problem solving, which means solving algebraically before substituting in numbers. I want to see, don't plug in numbers until the very end, because that helps us see relationships between things we could change and vary and measure in the lab. And then we'll get to step 15 in a second. Let's see. So solve for our finds is what we're doing. Let me remind myself, what am I looking for? I'm looking for that friction. I'm looking for that normal force. Let's start with the friction. I'm looking at this equation. This looks like a helpful starting place. Some folks are tempted at this stage to start saying, this is 15 kilograms. This is 0.250 meters per second squared. Do not do that yet. I want to see this equation rearranged, where one side of the equal sign is just the thing that we're looking for, and the other side of the equal sign is just the variables that you've listed in your givens list. Not the numbers. Those don't exist yet. Just the variables. So let's do that. Let's look for the friction. I'm going to start by rewriting that equation. We have MAX equals tension minus other tension minus friction. The algebra to isolate this looks like adding this to the other side of the equal sign and subtracting this. So let's go ahead and do that. We're going to subtract FTCA from both sides, and we're going to add FTCB to both sides. When we do that, the left side of this looks like MA in the x direction minus FTCA plus FTCB equals the friction force on the crate by the surface. And now I ask myself, am I ready to plug in numbers? Well, let's take a look. Here's what I'm looking for find in my find list. Great. Do I have 1, 2, 3, 4, all 4 of these variables in my given list? I have the M, I have the A, I can even make that an AX, I have the A, I have both tensions. Yes, we are good to go. Let's plug in numbers. I'm going to flip this so friction's on the left now. The friction force is equal to M was 15.0 kilograms. A is 0.250 meters per second squared. The tension force, its magnitude is all we care about now. The strength from Alice was, what was it? It was 55.0 newtons. And the tension force from Bob was 20.0 newtons. So we end up with a friction force with a magnitude equal to whatever that is. I need to grab a calculator real quick so that I can check on that. Oh, I see a mistake I made too. We'll talk about that in a second. Let's get a calculator first. So 15 times 0.0250 minus 55 plus 20. And I get negative 31.25. And that makes sense because here, this negative sign should have stayed with this here, here, here. And so the magnitude of my friction force is actually positive 31.25. I'm trying to think of sig figs here. Let's see. I'm adding and subtracting, so tenths place, this will be 3 sig figs, also 10th place. I should round to the 10th place. This will be 31.3 newtons of force. And that's the magnitude. If I want to find the full vector, which wasn't asked for here, but actually we can go ahead and demonstrate what that looks like. We put a vector arrow back above this, and we say this full force is 31.3 newtons, and its direction is to the left. And we put a box around that, and we say this is what my friction force vector is. Cool. So that's one of the two finds. The other thing that we need to find is the normal force. I'm actually running out of room here, so I'm going to go ahead and grab a separate piece of paper where we'll do the rest of this problem. So the rest of this, we're looking for, we'll just do it on this page upside down. This will work. The normal force. And we will grab that from the other equation we have here. So we have 0 equals the normal force on the crate by the surface minus the gravitational force on the crate by the earth. I want to isolate for the thing I'm trying to find, so I can subtract this over to the other side. I can say the gravitational force on the crate by the earth is equal to the normal force on the crate by the surface that I'm looking for. Am I done? Can I plug in numbers? No, I can't, because yes, this is in my find list, the normal force. But FG is not in my givens list, but M and G are, so we're pretty close. The last step here is to say that gravitational forces can always be computed as mass times gravitational field strength. So the normal force in this case matches gravity. That's not always true, but it is true here. This mass is 15.0 kilograms. This gravitational force is 9.81 newtons per kilogram is the gravitational field strength. Sorry, I think I said force there. G is field strength. The force is, from the normal force, matches gravity, so it's whatever 15 times 9.81 newtons per kilogram is, and we get 147.15 newtons, and we're going to round to 3 sig figs. That should be 147 newtons of normal force. I can put a box around that because I only asked for the strength of the magnitude, but if I wanted to take it a step further and tell you what the full vector was, I could say that this is a 147 Newton force vector that points upward. So add the direction, that now is a vector. There we go. And adding in the direction was step 15, our final step in this handout. There we go, and that answers the question. There is a lot going on. So the quick recap is picture, annotate it, VA, find points of contact, sign conventions, draw yourself a force diagram, read the question to list out what information is given, what you want to find. Write all your subscripts for your force diagram. Here, tell me, what is the net force equal to based on the motion? It's always MA. What is the net force equal to based on the force diagram? That's going to be specific to your context. Do that for the x direction and the y direction. Start with vector equations. Go to scalar equations, put them together. Finally, do some algebra as needed to isolate the thing you're trying to find in terms of the numbers and variables that you're given. Make sure to rearrange with algebra first before numbers get plugged in. I don't want to see numbers until the left side of the equal sign just says, this is what the question asks for, and it's equal to these variables. And we did that twice, once for the x direction to find friction, and once for the y direction to find the normal force. So that's how this works. Happy studies, folks, and enjoy. You got this.